Singh. I request Dr. Singh to start lecture. Dr. Singh, please.
Thank you. Namaskar to everyone. So I think in last lecture, I have discussed something called isometry of Rn. And I have also defined quickly at the end of our lecture what is meant by a symmetry group of any object inside Rn. So I will start my lecture by recalling some facts from last lecture, and I will continue in that direction. So now I will share my slide with you. Can you see my slides?
Yes, sir.
Okay, good. Thank you. Just 1 minute. Yes. So let us start by recalling what is meant by orthogonal group. Yes. So I have denoted it by the symbol O and R, and it consists of all matrices over real numbers, n cross n matrices over real numbers, with the property that A transpose is equals to identity, and A transpose A is also same as an identity. And in this case, we know that A transpose is actually inverse of the matrix A. So orthogonal matrices are the invertible matrices with more property. And inside the orthogonal group, I can define the special orthogonal groups, and which are all those matrices inside ON such that the determinant of the matrix is 1. Because from here you can directly deduce that if I take a determinant, then determinant is a multiplicative. So determinant A into determinant of A transpose is equals to determinant of identity. But determinant of identity matrix is always 1. So it forces that the determinant A into determinant A transpose is 1. And it also implies that either A is 1, determinant of A is 1, or determinant of A is equal to minus 1. So with respect to 1, this forms a very nice subgroup of ON, and it is called a special non-orthogonal group and denoted by SON. Now recall the theorem which we have proved in last lecture, that for any orthogonal matrix A and any vector in Rn, I can always talk about this function HAW from Rn to Rn. And what is this function? It says any vector V of Rn to AV plus W, where A is just A is a matrix A, and it sends a vector to AV. It's like vector V to AV. And sometimes we also write them as a T W composed with A, and it is like this. So theorem says that actually this function is an isometry, and moreover every isometry of Rn has this form. So using this theorem, we have seen the set of isometry in different way. And what was the different way of looking them? Just represent any element by C symbol. And what is the C symbol? It says that I can represent any isometry like this, A by W, bracket A by W, and it sends any vector V to AV plus W. And with respect to these symbols, it is very nice to compute what is the composition of these two symbols. Then it is easy to check that it is nothing but A1 by W1 composed with A2 by W2 is same as A1 A2 by W1 plus A1. So you can see quickly how it is done. So now I am interested in computing this at the point B. So what is this by definition? It is basically A1 W1, and definition of this says that it is A2V plus W. Now I want to apply this, so it will be A1 acting on this vector, so it will be A2V plus A1 W2, and again W1 will come here. So what is this? This is nothing but A1 A2V plus A1 W2 W1. And this is a translation part. So that's why I have written this composition as A1 A2. This is this one, and this translation part is this. And similarly, it is not very difficult to check that the inverse of yes, any question? No. So it is very easy to check that the identity matrix in terms of this symbol can be written like this, and inverse of any isometry of the type A by W is written like this. Now we can go and restrict ourselves for n is equal to 1. So n is equal to 1, Rn is nothing but the set of real numbers R. So now my aim is to understand what are the isometries of R. So what is your guess? What happened to? Yes, can you see my slides?
Yes, sir.
Yes, okay. Yes. So in case of real numbers, if you see what are the symmetries. So because in case of real numbers, O1R is plus minus 1. So it says that any symmetry is of the type AW. So it says V2 AV plus W. But since A is a matrix and it is a 1 cross matrix, 1 cross 1 matrix, and value is just plus minus 1, so it will be basically plus minus V plus W. So what it is doing, it is sending, suppose this is a real axis, suppose this is a vector V and W is a translation vector, so it is sending any vector V to V plus W. And what minus is doing, it is sending any vector V2 minus VW. So it means V is here, first you will come here minus V and then again translate by W. So this will be minus V plus W. So if you see clearly that the first one is giving you just a translation and second one is giving you first you reflect it and then translate it, which was the example of glide reflection. So you can see here in case of one. In case of R, the isometries are very simple and you have only two possible isometries. One is basically translation and second is just reflection and translation. So if translation vector is W is equal to 0, then it is just identity map. Now, interesting thing will come when we look the isometries of R. So again, how to geometrically see them. So we have seen that. Yes. So we have seen that any isometry of R2 is again written as HV is equal to AV plus W, where A is an element of O2R. So write A as just a matrix 2 cross 2 matrix A, B, C, D. Now use the property of orthogonal matrices. I know that determinant of A is plus minus 1. So hence we get A, D minus CD, which is the determinant of A, is equal to plus minus 1. Also, this property A transpose is equal to identity gives you this. And if you solve this, then you will get basically A square plus B square is equal to 1, C square plus D square is equal to 1, AC plus BD is equal to 0. And already you have a determinant AD minus BC is equal to plus minus 1. So which implies that actually A can be written in this form. So it means any orthogonal matrix, 2 cross 2 orthogonal matrix has this form, two possible forms. And you can easily check more because of this condition A square plus C square is equal to 1. It implies that this here small type 2 is there. Sorry. So this vector AC lies on the sphere, and I can write A equal to cos theta and B equal to sin theta, because you can also prove that B equal to actually C. So B equal to plus minus C. So here you can put this value and you will get the A is of the form this. So here small typos. So A is of the form this. So any orthogonal matrix is of this form. So depending on each two forms, we get different isometry. Now look what are those. So if you take A equal to cos theta minus sin theta cos theta matrix, then the map V goes to AV is always a rotation, and which rotates all vector through an angle theta. And if I take A equal to this matrix, then the map V goes to AV is nothing but a reflection map, and reflection is about the line L is equal to T cos theta by 2, T sin theta by 2. So what is mean by this line? So in picture, this line is this, which is making angle theta by 2 from x-axis. This is x-axis, this is y-axis, and this is a line about which we want a reflection. And what is a reflection? If you pick any point xy, then reflection map send this point to the Q. And how Q is calculated, I have given this in picture, and you can easily see that the coordinate of Q, which is suppose x prime y prime, then it is written like this, and which is this matrix we have already observed here. So corresponding to this matrix, we get a reflection. So now you have seen that when you start with any isometry, then you involve A. And now you realize that A has only two choices. And with respect to first choice, you got that it is a rotation. And with respect to second choice, you got that it is a reflection. So now, summarize everything in this table. I know any isometry is of this form, and depending on values of A and W, type of A and W, we get all these possible isometries of R. So it is identity when A is equal to identity matrix and W is equal to 0. It is a non-zero translation when A is equal to identity matrix and W is not 0. It is a non-zero rotation when determinant of A is equal to 1 and A is not identity matrix. And reflection if determinant is -1, and light reflection if determinant is -1 and W is not 0. So now here some more properties there, and that actually says that the line of reflection and the vector translating vector should be parallel or non-parallel. So this is very important also. So now recall again, I have defined what is a symmetry group of any geometric object inside Rn. It is nothing but the set Sx which has all isometries of Rn which preserve x. It means Hx is equals to x. And we have already checked that this is a subgroup of isometry group of Rn. So how to check? To show that it is a subgroup, it is only enough to check that if I pick two elements in this set, then suppose element is H and G, then H G inverse is also here. That is a criteria to check subgroup. And now it is easy to check that for H and G. Now I want to show that HG inverse is here. It means HG inverse of X is equals to X. So for that, you can easily verify that this set is a subset of this. And since they are bijection, so it will be exactly equals to X. So how to check? So let X be any element in capital X. Since G is a bijective map, so it means Gx is equals to X. So for X, there here typo is there. So for X, there exists a Y in capital X such that Gy is equals to X. And since G inverse X is equals to G inverse composed with Gy, that is equals to Y. So we get actually H composed with G inverse X is nothing but Hy, and hence it belongs in X, Y, because Y belongs in X and X is equals to X. So thus we have proved that this composition H composed with G inverse is also element of this, and it implies that this subset is nice and it is actually a subgroup of isometric group of R. And we denote this set group as a symmetry group of any object in X. So now I have recalled whatever I have finished quickly in last lecture. Now our aim is to compute what is a symmetry group of a regular polygon. If you have any question, you can ask me before calculating. So I assume that there is no question. So now our aim is to calculate what is the symmetry group of a regular polygon. So before doing this, just some few observations. Suppose note that all points in the plane at a fixed distance from a given point, suppose two given points are there, A and B. And now my question is that I want to find out all points P which has a fixed distance from A and B. Of course, a point which has a fixed distance from a particular point A forms a circle. And if you consider all points which has a fixed distance from two given points, then they are basically the intersection point of two circles. So in this picture, suppose A and B are 2 points, and I'm looking all those points which has a fixed distance from A and B. So now I have constructed the intersection of two circles, and you can see easily that P and Q have a given fixed distance from A and B. And it will be at most 2. It may be 1 also when the circle intersect at only 1 point. And there is also possibility that you don't get any point with a given fixed distance if they don't intersect. But whatever happened, it will be at most 2. That is very clear. So now theorem we are going to prove that let X, yes.
Sir, the distance from the 2 points is necessarily be same, or they can be different?
No, it can just any fixed distance. Maybe from A, suppose distance is 2 centimeter, from B it can be 7 centimeter.
Okay.
And that's why all 3 possibility can occur.
Okay, sir. Okay.
But my interest is whatever possibility occurs, it will be at most 2. That is my interest. Okay. So now let Xn be a regular polygon with n edges in the plane. Then my claim is that the size of this group is always 2n. That is my claim. So for example, if you take triangle, then what is the symmetry group of this? How you calculate the symmetry group of this object? So we have seen that, okay, to calculate the symmetry group, we know that what are the symmetry of R2. They are basically rotation, reflection, or glide reflection. But I am saying whenever I have any bounded shape inside Rn, then translation will not come in picture. Because translation, if translation is coming inside isometry, then it will shift the object. So position will be changed. And in isometry, it is not allowed. If it is a bounded, then position will be changed and it can go beyond the limit. So only possible is isometries of any bounded shape is basically either rotation and reflection inside R2. And now you know what are the reflection and rotation, so easily you can calculate, okay, if I take this line and I reflect this triangle about this line, then still this reflection give me an isometry of R2 which preserves this triangle. Similarly, if I take this point as a origin and I rotate this as 120 degree, then still I get a same angle. But if you see more closely, then I am saying that we need only few points to check. And what are the observation? First observation is that isometry fixes the centroid of any shape. So suppose you have a regular shape, then I can always talk about what is the center of this regular shape. So like in case of equilateral triangle, you know what is the center. In case of a square, you know what is the center mean. So whenever you have a regular polygon, then I can talk about what is the center. And since each isometry preserves the center, so without loss of any generality, I can assume that my center is always an origin. If not, then I can do some more translation and we can always assume that it is an origin. Second, whenever I take a polygon, then where vertices goes? Where vertices always goes to the vertices. Yes. And any, which I have already mentioned, that any isometry will be of the type HV is equal to AV, where A belongs in O2R. And fourth property, that any line segment will go to the exactly the line segment under the isometry. Why? Because we know isometry is a linear map. So under linear map, if I know 2 points are going to 2 points, then their linear combination will also go to the linear combination because of linearity. And hence line segment is going to line segment. So final remark is that to understand the element of symmetry group of any regular polygon, it is enough to understand the image of vertices. Because when we fix vertices, then other points are the linear combination of these vertices, and then we can use the linear combination and linear property, and we can write down the image of all other points on this polygon. Okay, so for any question on these observations?
Sir, please explain this part again, that why there is no translation.
I suppose a translation is there.
Sorry?
Suppose in picture, suppose this is object. Okay?
Okay, sir.
Some translation is there. Suppose you are translating by some vector. So it will translate and come here.
Okay.
So, but position is now changed, no?
But sir, the overall shape that remains the same.
Yes.
Then why we are facing some problem in having a translation?
No, shape is same.
Because the overall
shape will be always same, because translation is also isometry. But I am saying that position is changed. So you say what is the isometry of this, a subset in R2? What if X is just 0, 0? What is isometry means? What is the definition of Sx? It says that all H such that X is equals to X. It means H0 is equals to 0. So whenever I talk about the symmetry group, I am saying the position is also fixed. Of course, point will
Okay.
go to the point. So in that sense, all symmetry will play role because all symmetry is sending point to point.
Okay. Okay.
But when we talk about the symmetry of a point, means you are fixing that point. So position is important.
Okay, sir. Now it is okay. Yes. Thank you, sir.
And that's why translation, whenever you have a bounded set, then translation is not coming a picture. But of course, translation is not disturbing anything. Distance wise, it is preserving. But position of this is moved. So they are not taking part in that sense. Okay? Even they take, you don't care too much because whenever you apply translation, you will get exactly same thing. So there is no loss. Okay? But we just exclude them because we don't know.
So
They are very nice, you can say. Yes? Can I move?
yes, sir. Thank you, sir.
Okay.
Yes, sir. Yes, sir. Please.
Yes. And now another observation that if the point on a regular polygon is determined among the all points on the polygon by its distance. So suppose I am interested, suppose this is a point and I am interested to understand what is its image under the isometry. So first I am saying the position of this point is always determined by the other vertices or other points on the regular polygon. Why? Because I know, suppose I fix these 2 points, P and Q, which is a side of like here. In this, suppose I assume that this is my edge A and B, okay, on my regular polygon. Now I want to know the position of other vertices or other points on the regular polygon. So I know their distance is fixed from these 2 points. Of course, if polygon is there, then any point has a fixed distance from given 2 points. And if it has a fixed distance, then you have seen that in a plane, there is only at most 2 possibility that point can come in picture. And one is like here and another one is like here. So either one side or, so what is the possibility? What is the possibility that either it can be here or it can be here? Because your polygon is a convex and it is made by lines. So some points may lie exactly one side of the line. And that's why the position of all points determined by the other point on the regular polygon. So now, for example, in picture 2, which I have already mentioned, this, okay. Okay, so this step is again clear. Now, what I'm doing, I will take 2 points P and Q on, suppose this is my object. This lines, curve line doesn't mean that it is a curve. It is of course a straight line. It just tells you that I don't know how many edges are there. So they represent unknown edges which we don't know, and here also. So now it means it is a polygon, and these curves means some straight lines which we don't know how many are there, and it is for in general any and regular polygon. This is my picture. Okay. So now I fix 2 points on this polygon P and Q, and another point R. Now I want to understand what is the image of P and Q and R under any isometry H. Okay. So suppose P is going to some point HP. Assume that P is going to some point HP. Then what is the possibility of the image of the point Q? Anyone can answer me? Hello? So yes, so I am saying the under isometry, the adjacent vertices of any polygon also go to the adjacent vertices. Otherwise, because under isometry there is no change in the shape size of the polygon. So if the point Q is adjacent to P, then under isometry, suppose P goes to HP, then Q will go to definitely HQ, which is adjacent to the HP. Q doesn't go like here. Suppose PQ is here and H is an isometry, then Q doesn't go like here. Q doesn't go like here. Why? Because P and Q are adjacent and their distance is fixed. So whatever will go, it will be some edge which is coming from HP. I am saying like this. So it will be adjacent to the HP. It's fine. And when it is adjacent to the HP, then what about the point HR? So for any other point HR, since it has only one choice, which we have seen that any other point on the regular polygon is completely determined by the exactly two vector on this polygon, two points on this polygon P and Q, and hence, so now I will say again what I already said, that pick two adjacent vertices of a regular polygon and call them P and Q. As in the figure this, an element H of HXN, symmetry group of XN, is an isometry. So it is taking the regular n back to itself, and it must carry vertices to vertices, and H must preserve the adjacency of the vertices. So HP and HQ are the adjacent vertices under the isometry H of a polygon. Now for each R on the polygon, the location of HR is also determined by the location of HP and HQ. Why? Because R has a fixed distance from P and Q, and hence the HR has a fixed distance from HP and HQ. And since HR has a fixed distance from HP and HQ, then choice can be only two. And I mentioned you that this will be actually in this case only one, because it will lie exactly one side of the line segment HQ, HP and HQ. So now to compute the order of the group, symmetry group of regular n xn, it is enough to understand the possibility of image of P and Q, or basically the number of possibility for HP and HQ. Now, where will P go? Suppose it has n vertices, then what will be the choice of P under this any isometry? It can be any vertices. So this vertex P can go to the any vertex, and that's why it has a choice n. Now, what about the choice of Q? Since HP is fixed and Q is adjacent to P, and from HP there are only two sides. Adjacent sides are either this way or this. So HQ has only two possibility. Either HQ will be here or HQ will be here, because it should be adjacent to the HP. And hence, the number of choices of HP and HQ is basically less than equals to n into 2, which is 2n. And that's why the order of this group is always less than equals to 4. So far, any question? No. So if there is no question, then now in next step, I will prove that corresponding to each number between 1 to 2n, I can always find out some isometry, and that's why we get exactly 2n isometry of any regular polygon. Now question, how to get this? So first I will find out the rotations. So a regular n-gun can be rotated around its center in different way to come back to itself. And how it can be done? So suppose you have this polygon, regular polygon. So what will I do? Because it has, so I can divide these angles. And I know all these angles are same. And actually these are 2 pi by m. These angles. So now I take this angle, and then I take this angle. Now I take this angle. Again, I take this angle. So I will call them a 2 pi k, where k is varying from 0 to n minus 1. So if I rotate my picture by this angle, then there will be no change in this picture. And I can do this in n different way. And these are the actually all possible rotations of the all possible rotations, which gives you the symmetry, which are the element of the symmetry group X and now corresponding based on the number n odd and even, I will try to construct reflections. So how to do this? So for n is equal to odd, I can get this picture, because here n is 3. I get this picture, which is n is 5, and similarly for other. So how to construct a reflection? For reflection, I need a line across which I want to define what is a reflection. So in this case, whenever you have an odd number of vertices, then I will take one vertices and take opposite edge and take its midpoint, and the line joining the one vertex and the midpoint of the opposite edge is the basically line of reflection, or you can say line of symmetry. Of course, in this picture, if I take this line and I reflect I define a reflection about this line of R2, then it is very easy to check that this object is preserved. There is no change in this object. The image of this object will go exactly to same, and hence we get an element in the symmetry group of this triangle. Now again, I take this vertex, I take a midpoint of opposite edge, and then take this line and this, and thus we get exactly n reflections. Why? Because each reflection is determined by the one vertex. And since it has an n vertex, so I will get exactly n vertex. Now I will explain how to get reflection when n is equals to even. It means when we have an even number of vertices. So in picture, this is the case where we have an even number of vertices, and which is exactly 4 in this case. Here we have a 6. 1, 2, 3, 4, 5, 6. So in this case, what we'll do? First, we'll take 2 opposite vertices. So like in this case, what is mean by opposite vertices? If I take this vertex, then this is opposite one, and I take a line joining them. And with respect to this line, if I define a reflection of inside R2 of plane, then we'll see that this picture, this part will move, this part will move here, and this part will move here, and eventually you will get this whole picture is preserved under that reflection. And thus this reflection about this line is always an element of symmetry group of this square. Similarly, I take 2 edges, opposite edges, and join their midpoints. So I will get a line. And again, this line, with respect to this line, I can define a reflection of a plane, and we see that this part will come here, and this part will come here, and again the picture will be same. So this reflection is again gives you an element of symmetry group of square. So now count these numbers. So when I take one vertex, then I am also fixing the opposite vertex. So when n is even, then how many choice I have? I have n by 2 choice, because 2 vertex count 1 reflection. So I get a n by 2 reflection taking vertex to vertex. Now when I take edges, then 2 edges counts 1 reflection. And what is the line? Line is basically joining the midpoints of these 2 edges. So I will get exactly n by 2 reflections, and now total I get exactly n by 2 plus n by 2, that is equals to n reflection. So in both cases, when n is odd and n is even, I get a n reflection. Now you can ask that maybe some reflection is same as a rotation or some rotation is same as a reflection. But it is not the case here. Why? Because we know where the rotation is coming by matrices of determinant 1. Reflections are coming by matrices determinant -1. And clearly in picture, if I take this reflection, then this point is preserved. If I take this reflection, then this point is going to the same point. Even this point is going to the same point. So that's why the reflection about this line and reflection about this line are also different. So I proved that these reflections are not same as rotation. And even if I take two reflections here, then both are different. So it means I get n distinct reflection. And in previous discussion, we got n distinct rotation. So how many I got? I got exactly 2n. And in step before, we have proved that actually it can at most 2n, and I have produced exactly 2n. So it has that. So thus we proved that the cardinality of the symmetry group of the regular polygon is exactly 2n. Now we'll write some more information in this symmetry group. So if I write this one rotation R, which is a rotation corresponding to the rotation of angle 2 pi by n, then it is easy to check that other rotations can be written as just a power of r, and they are nothing but I2 r, r square, r power n minus 1. So what is rk? Rk is basically rotation about the angle 2 pi kn. So this one was 2 pi by n, so this will be 2 pi kn. So I can write them like this. Now if I take let S be a reflection across a line through a vertex, some one vertex you fix. For the simplicity, always we take a vertex on a x-axis, but we can take any and then take a reflection across that line. Then it is easy to check that because it is a reflection, so x square is 1, and hence the inverse of this reflection is same as it s. So like in this example, whenever I take a vertex, I can consider a reflection, and if I take first this point goes to here, and again if I take one more time image of this point, then it will come back here. So it means s square is equal to identity. So now write down these elements s r power k. Then it is easy to check that no s r power k is a rotation for any k between 1 to n. Why? Suppose it is a rotation, then it will be written as s r power k is equal to r power l, where because all rotations are of the type this. And this implies that I can write s is equal to r power l minus k. And what is mean by this? Because this is a rotation and this is a reflection, and this is not possible. Why? Because determinant of reflection is -1 and determinant of rotation is 1. So this will never happen, and hence these are not a rotations. So, and how many are they? They are exactly n. So they will be definitely a reflection. So thus I can write element of this set like this: s power I, r power j, where r power n is equal to identity and s square is equal to identity. Also, you check that this is a reflection, so this square is equal to identity implies that SR is equals to R inverse S, and hence I get this solution. So now this is a very nice description for the symmetry group of regular and we actually define this as a dihedral group for n is equals to greater than equals to 3. because if I take n is equal to 2, so there is no polygon which has a closed polygon which has a 2 sides. So this is always defined for n is greater than or equals to 2, and this is a group which we call as a dihedral group, and which came from geometry. But this description helps us to define this dihedral group actually for any n, and we write like this. And actually we denote by this dn or d2n depending on different group. They use both notation. So in my lectures I will use dn, and I can define dn as just the symbols xi yj's, x power I y power j, such that I is varying from 0 to 1 and j is varying from 0, 1 to n minus 1. And how to define the product? To define product, we need some more property on these symbols, and now assume this property that xi yj is equals to xk yl if and only if this I is equals to k and j is equals to n. And second, x square y power n is always identity. And third property, you assume that xy is also same as y inverse x, that is yxy is equals to x. And you see that all these were here. So just taking these, I have defined abstractly what is dn, and dn is now in this definition dn is defined for any n. I don't need to put n is greater than or equals to 3, and it is very easy to check that actually d1 is isomorphic to z2, d2 is isomorphic to v4 which is a Klein 4 group, and d3 is isomorphic to s3. So far any question? So I have told you why dihedral group and what is a dihedral group. Actually it is a dihedral group coming from the symmetry group of any regular n-gun, and abstractly I can define them like this. So any question? Otherwise I will move to next topic. So now I will discuss the finite subgroup of O2. And now I will try, and after that I will connect them to again how they are related to the symmetry group of regular polygon. So theorem: a finite subgroup of SO2 is a cyclic group, and a finite subgroup of A2 which is not contained in SO2 is isomorphic to the dihedral group Dn for some. So how to prove that? It's very simple. Suppose G is any finite subgroup of SO2, then of course since SO2 is a all matrices with determinant 1, so whatever symmetry isometry I will get from there, they will be basically rotation and rotation matrix, and these are completely determined by the angle theta. And suppose theta is the smallest in all element of G, and this I can always find. Why? Because G is a finite and each element is associated to some theta, so I can choose which one is the minimum between all of them, so call them theta. So let in picture this is a theta. So now let R be any other rotation, so let R be the rotation with respect to the smallest possible theta. And now consider S be another rotation inside this group. Since it is a rotation, so it will be associated to some angle. Suppose this is a rotation with respect to the angle phi. It means it rotates any element angle phi. So of course phi will be always greater than or equal to theta. Why? Because theta was chosen minimum. So now I can always write phi is equal to n theta plus psi. So what I will do, I will take theta, again I will take 2 theta, 3 theta, 4 theta, and I will try to reach at phi. And I will choose the maximum n such that I can come to closer to the psi. Okay. So now look back this psi. Of course, if psi is greater than theta, then I can choose n bigger, but n is the bigger one, so definitely psi will be less than equals to theta. Now look this rotation s r power -1. This is a rotation. What is the rotation? This is a theta, and now this is a phi, and this is a n theta. So this is a basically rotation related to r power n. So now what I am doing, I am going by s, rotating any element by phi, and then coming back again n theta. So I will come. So this is basically the rotation associated to psi, rotation of psi. But psi is the smallest. Psi is smaller than theta, and theta was the smallest in the group, and this element is also inside the group, so it forces that psi should be g, and this proves that s is equals to r power n. It means any element of this group g is written as the power of a rotation r, and hence this group is actually cyclic. And similarly, it is not very difficult to show that if this group is not contained in SO2, so means there exists some element in O2 which is not in SO2, then we can prove that actually G is isomorphic to T. So what is the conclusion from here? Conclusion is that now what we have done, we have saw that if I take a regular polygon, then its symmetry group is nothing but T. And now I have taken a SO2, O2, and I looked what are the finite subgroup of this. They are exactly cyclic group or D2A. So this means this regular gun and the finite subgroup of O2, they have some bijection, and they are related to each other. So if any finite subgroup of this is actually a symmetry group of some object in R2. And what are they? They are actually regular. So far any question? No. So it is very difficult for me now to cover many things. So same question you can ask, what can we say about in R3? And what are the subgroups of SO3, finite subgroup of SO3, and how they are connected to the symmetry group of some objects. So again in R3, we have a very remarkable fact that if I take finite subgroup of SO3, then they are actually either a cyclic group or dihedral group or one of the groups associated to the Platonic solids. Because in case of R3, we have proved that what are the regular convex polyhedrons? They are nothing but Platonic solids, and they were exactly 5. So any finite subgroup of SO3 is just a cycle group Dn or group associated to Platonic solids, and they are actually exactly 3, and they are actually similar. The word we can use like a dihedral, they are called as a tetrahedral, octahedral, and icosahedrals. So now the finite subgroup of SO3 is related to again the symmetry group of some nice object inside R3, and these nice objects are especially Platonic solids. So I will not do much in this portion, and in next class I will change my topic and I will say something about the equivalence relation and group action, and I will give some application of them, and I don't think I can do more than that. So now I end my today's lecture. If you have any question, doubt, you can ask me. And I'm keeping most of the thing in my notes, so if you have interest, then you can see.
Thank you, Dr. Singh. Any question from participant side or curiosity you can ask if you have. Okay. I think no
Sir,
queries.
sir,
Yes, you can ask one
Yes.
question. Yes.
can we have your email ID so that if we can have some question afterwards, we can email you?
Yes, yes, definitely, definitely. I can write in chat, or
Please,
you
sir.
can you can see in chat box my email ID.
Thank you, sir. I got it.
Okay.
Yes,
Okay.
actually there are many things, but because of time limitation, you know, it is very difficult to explain most of the thing. But this is a very good topic in the sense you can ask the question now also in very whatever, like in many folds, in many other places. What are the isometric group of any Riemannian manifold or manifold or something like that? So such type of questions always exist there. Even you can ask question also, okay, now we have done polygon, now we have done a polyhedron in R3. What about the polyhedron in Rn? And now question again, how many regular convex polyhedron will get in Rn? This question you can ask. Then again you can ask, okay, now because we have seen that they are related to finite subgroup of SO3, SO2. So what about the finite subgroup of SON? And can we explain them in terms of a symmetry group of some nice object inside Rn? And such type of question you can ask, and of course we have answer of all those questions. And also you can go more, because in beginning I used the definition of metric spaces. So I say what is mean by distance preserving map inside the for metric spaces. So you can ask similar questions in metric spaces. What are the isometric group of any metric space, and then continue. So still more work is going on in that direction. And of course, if anyone is interested, then we can, I can provide you details about that.
Thank you, sir.
Okay. Any other?
Excuse me, sir.
Huh.
Yes.
Can you just repeat once again the part of finite subgroup of SO2, that part?
So in my theory, today I have proved that what are the finite subgroup of SO2. So I proved that the finite subgroup of SO2 is nothing but a cyclic group,
Yeah, okay.
nothing else.
Nothing else.
If I take a finite group of O2, then of course it is a cyclic group. Order can be anything, okay? And also it is a dihedral group.
Okay.
And what is SO2? You just try to find out what is SO2. Then you will realize what are the finite subgroup very easily.
Okay, sir. Okay.
Is it circle group or something like that? If it is a circle, then what are the finite subgroup of any circle? They are just a finite points with equal angles like that.
Yeah,
So,
okay. Definitely.
yes, there are many ways to look such objects.
Okay, sir. Thank you.
Okay. Thank you. Thank you so much. Let us thank Dr. Singh for a nice material and nice lecture, for providing us. On behalf of all the participants and DW, I would like to extend sincere thanks to Dr. Sanjay Kumar Singh, and let us clap for Dr. Singh. Thank you so much. Thank you all, and we will meet tomorrow at 3:30 p.m. for tutorial and as well as the lecture of Dr. Singh.
Yes, just one more announcement. Sorry.
Yes.
There are some problems in problem set which assume your knowledge in group actions. Okay. So even you can do, because you have already done equivalence relations, so you can do that. But if you know some more definitions related to and some more proper facts related to group action, then you can easily solve them. So, but yes, now tomorrow is my last lecture. I was thinking to finish some part today, but yes, I couldn't do. So now you know how to manage your problem set.
Okay. Okay. Thank you. Thank you, sir.
Okay, thanks.